Hello and welcome to video lesson 10 about deformations in axially loaded members. Our learning objectives for this lesson are to derive the equation delta equals PL over AE for axially loaded bars, to solve problems requiring use of the equation delta equals PL over AE, and to apply superposition to solve indeterminate problems. For this lesson, you should be reading Beer and Johnston's section 2.2. So let's get right into the derivation. This equation results from the application of basic definitions in mechanics of materials. For the 1D bars, we have defined axial stress as P over A. We've defined strain as delta over L. When we substitute P over A in for sigma and delta over L into epsilon in the equation for Hooke's law, we end up with an expression that says P over A equals E delta over L. Then that reduces to delta equals PL over AE, which is the equation that we will be working with. So let's do a brief example showing the use of that equation. In this example, we have a steel rod of 2-inch diameter, 20 inches of length, that's subjected to a load P at the end of the shaft. And we'd like to know what P is required to cause a deformation of 0.1 inches. So we know that delta equals 0.1 inches. That's equal to PL over AE. I know L, I know A, and I know E, or I could easily find them from the problem information. So I want to invert this to solve for P. So P is equal to AE over L times delta, which is another equation that is worth memorizing, because you could use that in quite a few indeterminate problems later on. So when we plug in everything that we know, we would say that P is equal to pi over 4 times the diameter of 2 inches squared times Young's modulus of 30 times 10 to the 6th pounds per square inch times the required 0.1 inch deformation divided by the length of the rod, which is 20 inches. When we punch through the numbers, we would find that P is equal to 471,238 pounds, or 471.238 kips. Now, we could extend this concept to a little bit more general situation with stepped shafts, like the one you see here. I have 2 sections. Each section has its own length, cross-sectional area, and Young's modulus. These need not be the same material. And the second shaft has its own length, area, and Young's modulus. And we have loadings of P1 and P2 on the shaft. That means we've got a support reaction of P1 plus P2 at the fixed support at A. So if I wanted to figure out what the total displacement delta was for point C, that would be the total deformation of the shaft, and that would be the summation of PL over AE for each part of the shaft. So if I was to take a look at the internal force in section AB, that would be P1 plus P2. So applying that formula for section 1 of the shaft gives me a contribution to the total deformation of P1 plus P2 times L1 over A1 E1. And then to that, I should add the contribution for the second part of the shaft, which would be P2 L2 over A2 E2. And I could consider each part individually. So delta 1 would be just the extension of shaft 1. Delta 2 would be the extension of shaft 2. Let's put some numbers to this. So for the above shaft, we want to know the total extension when P1 is 10 kips, P2 is 5 kips. We'll assume both bars are made out of the same material, which would be a steel. So we would have Young's modulus of approximately 30 times 10 to the 6th psi, or 30,000 ksi. L1 will take as 20 inches, L2 will take as 15 inches, D1 will take as 2 inches, D2 will take as 1 inch. So when we plug all of those numbers into our equation for the total displacement, you would see that we have a total displacement of 0.00637 inches. So we've seen how to calculate deformations for single shafts. We've seen how to deal with more complicated situations. And this is all important because calculating deflections is important, but by being able to calculate deflections, we can solve indeterminate problems, which is the thrust of Beer and Johnston section 2.2. So let's take a look at superposition. Whenever we want to apply superposition, we have a structure that has more redundance than we have available equations of equilibrium. And in this case, we have a support reaction at the left fixed support and at the right fixed support. And we only have one useful equation of equilibrium that would say the summation of forces in the x direction equals 0. So, well, how do we handle a problem like that? We know that it's got to obey all of the principles of statics, but there are an infinite number of combinations of the left and the right reaction that would add up to P. So the way we figure out what specific combination of RL and RR that adds up to P we would actually have for this structure is to pretend that the right reaction, or you could pretend the left reaction didn't exist, but in this illustration, we're going to take the right reaction as the redundant. And we would remove it, and we would keep everything else the same in what we're going to call the primary structure. And we would calculate the deformation of the primary structure at the point where the right loading is, the right support reaction is going to be applied. And then we would superimpose on top of this solution a solution where the redundant is applied, and the redundant is allowed to push the structure back to a point where the deflection of the free end is equal to 0, as it must be for this structure here. So what we would have is delta P plus delta R equals 0. Delta P is a rightward deflection. Delta R is a leftward deflection. So when we add them, they add to 0. And then the right reaction plus the left reaction has to be equal to P for static equilibrium. So what we would like to do is to solve a problem. We'd like to determine the left and the right reaction when L1 is 30 inches, L2 is 70 inches, and P is 10 kips, and we're going to assume that AE is constant for the whole bar. So this is our solution to that problem. You can see that L1 is 30 inches, and L2 is 70 inches, and P is 10 kips. And we're going to take the right reaction as the redundant, which means we're going to pull it off. We're going to let the structure deform. And you can see that only the red shaded area in the primary structure is carrying any axial force, and that axial force is actually P. This green shaded region out here is not carrying any axial force. So that part of the beam is going to just go along for the ride as the beam extends outward, as it deforms outward. Then what we will do is we will apply the right redundant reaction on the redundant structure, and we'll add these two solutions together. So we would have the right reaction that would push inward, and the whole bar is going to carry a force of RR. So the whole bar is going to undergo strain and is going to be under stress. So we're going to have to enforce, and we should do this before we do equilibrium. We can do equilibrium after we have got this. We should work with our compatibility relationship first, because it's going to isolate the right reaction, and we would have two unknown reactions if we just tried to do equilibrium first. So we're going to work with the compatibility equation. For in this particular instance, we're going to work with this first, and this will isolate the right redundant. So if I was interested in delta P and calculating delta P, what I would have is P times L1 over AE. And that would be 30 inches times 10 kips over AE in magnitude, or 300 inch kips over AE. Delta R would be equal to negative, because it's going to the left, RR times L1 plus L2 over AE. That's going to reduce to negative RR times 100 inches over AE. Then I have the compatibility equation that says delta P plus delta R has to equal 0. So 300 inch kips over AE minus 100 RR over AE equals 0. And that's going to give us the solution that RR equals 3 kips to the left. Then when I consider the summation of forces in the x direction equal to 0, the equilibrium condition, I would have 10 kips minus the left reaction minus the right reaction equals 0. That gives me 10 kips minus the left reaction minus 3 kips equals 0. And when I solve for the left reaction, it is 7 kips to the left. That's all for video lesson 10.